Here we are at the very end of the ZEOCAT-3D project, and after 4 years of the development and achievement of most of the targets of the project, we can say that we get very relevant and interesting results.
ZEOCAT-3D is a European-funded project related to the catalytic transformation of hydrocarbons. The project started in 2019 with the aim of establishing an alternative route for the conversion of methane from natural gas and biogas into benzene.
One of the results that we get in the ZEOCAT-3D project is the development of a potential patent in catalyst materials development. In the project, we also used DLP with materials based on zeolite. It is also relevant the use of membrane systems for upgrading and in the upstream part of the biogas treatment.
In the concept of ZEOCAT-3D, we had to integrate 3 units that perform different processes. This upstream conditioning unit employs the technology of wet membrane gas absorption, and with pure water we have the ability, the chance to absorb carbon dioxide from the biogas stream, and with the same process we can also dissolve carbon dioxide. The main result of this unit is 2 complete purified streams, one with pure biomethane and one with pure carbon dioxide.
One of the results of the modeling activities is an application for the catalytic reactor in which we can better understand the behavior of the catalytic reactions inside the process.
In the frame of the ZEOCAT-3D project, we have developed this catalytic reactor app, which serves the purpose of bridging the size scale between the process at catalyst scale and the process at kind of flow scale of the whole device. And so the goal was here really to help in upscaling when we try to bridge from the very small scales where the chemical reaction happens to the larger process scale. And especially for that purpose, we have improved the app to be more versatile and more useful in this upscaling process. With this new version of this app, we are now able to better include different boundary conditions and flow scenarios which might appear in the real-world application.
We provide also some advances in the characterization of nanomaterials.
It is very important to do the characterization of the catalyst, but also of the spent catalyst, because this will give you insight about the mechanisms involved during the reaction and how you can improve your catalyst but also optimize the process. So we think that probably it will be very useful for the industries to provide a complete tool which is the characterization of materials. Could be either for the raw materials or the spent catalyst. Actually, for this reason, we try to prepare this CWA, which is a CEN workshop agreement. The purpose of this document is to promote our efforts on characterization, but to prepare a document like a white document for the characterization of the catalyst, and to be probably further facilitate the formation of a new standard on materials characterization, on nanoparticles characterization, on catalyst evaluation.
We have also very relevant results in the regeneration of the catalyst.
It is difficult to prepare catalysts that can have a very long period of utilization without regeneration. But this is something that it's from the technological point of view. This is already exploited during the project, and I think the solutions provided in work package 4 are very relevant, and we can let's say advertise this to the industrial partners that they can use a certain methodology in order to avoid the cork formation and to use this type of catalyst.
We have also advances in FSP technology. On the one hand, it has been possible to produce very specific and complex nano-catalyst compositions based on molybdenum. And on the other hand, the obtained active nanopowders have shown high versatility for their combination with zeolites and impregnation on monoliths. It is also very relevant the obtain of hydrogen as a subproduct of the process because of the energetical context in which we are at the moment.
Hydrogen which is produced from ZEOCAT is in pure form. It can be used as it is produced or further stored with the aid of naphthalene, which is a co-product of the reaction and used later when there is the need for energy. So in this way we use, let's say, green hydrogen because it comes from biogas.
It has been a long journey in these 4 years, and we had our ups and downs in the process. We also faced the COVID disadvantages because we had to deal with working or not working at the lab. But at the end, I think that we achieved most of our targets and objectives, and we also developed a very good networking among us. So we are quite happy with the results.